In this section, we're going to look at directing groups. How do we substitute different groups onto an aromatic ring? This is a really important step in the synthesis of new aromatic chemicals. With benzene, it's quite straightforward to substitute one of the hydrogens with something else, like bromine. And this is called bromination. If you go back about 3 lessons ago, we looked at the electrophilic substitution of bromine with one of the hydrogens that are on the edge of the ring there. Now, electrophilic, that bromide ion was attracted to the high electron density of all of those electrons in the pi system of benzene. But once it got in there and replaced the hydrogen, what it has done is it's actually sort of subdued. It's calmed down the electron density in that area because it is basically an electron withdrawing ion. So what it's doing is in that area, the electron density of the pi system is no longer as strong as it was before. Now it means that the benzene ring is not as attractive to electrophiles as it was before, and it normally requires higher energetics to make the substitution happen. So the conditions need to be changed to get the di substitution. And this is because the benzene ring we describe as being deactivated. Its electron density has gone down. Now, even though it has gone down, another substitution could occur, but it's going to happen at the place where the pi system has had its electron density reduced the least, on the opposite side of the benzene molecule. So what you can see, it's quite often that a second substitution would occur, but possibly on the other side. And what we're going to look at in this lesson is the rules of engagement, where things can and will attach as a result of the changing of the electron density of the benzene pi system. Let's take a look at this. This is phenylamine. So this has got it's a benzene ring with nitrogen and 2 hydrogens attached. Now, this is a species that actually activates the ring. The nitrogen has got lone pairs of electrons, and what they do, they're sitting there next to the electrons in the pi system, creating a higher electron density in that region, making the whole thing more attractive to electrophiles. So what you're going to get is an enhancement of the attractive properties of this molecule. And quite often, substituting species like bromine, for example, they're going to try and bond on the carbons adjacent to the place where the electron density is highest, in this case right next to the NH2 group. So for that reason, you're going to get most likely the first substitution occurring in the 2 position, immediately on the next carbon. Now once you've got one there, you're going to also find that you're going to have the next substitution. The presence of the bromine would ever so slightly lower the electron density near there. So you're going to have the next substitution, the di substitution, occur as far away from the first bromine as it can physically get, but also in a place of high electron density relative to the NH2 group. So you find that most likely in the 6th position. So you've got one flanked either side. But then you won't necessarily get one in the 3 and 5 position, that's too close to the first 2, but then you can get one, then substitute for a tri-substitution in the 4 position, straight down. And so what you can see is, once activated, we get a filling pattern of substitutions around this aromatic ring. And this filling pattern is quite strict. We normally get a substitution occurring at positions 2 and 6, and it could be 6 and 2. And we'll explain why it could be that way around in a second. But basically 2 and 6 are equally likely, and then 4 afterwards. What we won't get is this picture on the right, where it's filled positions 2, 3, and then 4. It doesn't happen like that, because that's not following the rules. You would not get that happening in that order. It would be 2, and then 6, and then 4. Because ultimately these substitutions, they're electrophilic. They're attracted to electrons, and they're attracted to the place of the highest electron density. And the presence of that NH2 group is making the electron density higher in certain places. If we change the NH2 group into an NO2 group attached to this benzene ring, then something different happens. Take a look at this. This is nitrobenzene. The NO2 group is attached at the top. Now the NO2 is really strongly polar. The oxygen that is attached with a single bond has a negative dipole relative to the positive nitrogen that is ultimately attached to your carbon. Now the presence of a strong negativity towards the oxygen end and strong positivity towards the nitrogen end makes that little corner of your benzene ring have a lower electron density. It makes that area less electron rich than the rest of the ring. It has what we describe as deactivated the ring. It has made the ring at that position significantly less electron dense. It now makes positions 2 and 6 very unappealing for electrophiles. They're not going to go there because there's not that many electrons, and also they're not going to go opposite. What is going to happen instead is they're going to be forced to go into those places least affected by this draining of the electron density, positions 3 and 5. So if the group that's attached to your benzene ring deactivates, lowers the electron density, it's a 3 and 5 position that the subsequent substitutions are going to occur in. If it activates it and it enriches the electron density, then it's a 2, 6 and 4 position. Now we can use this information to our best advantage. So you may ask yourself, why are we so bothered about this? Well, these different structural isomers actually have different properties. They'd have different boiling points and melting points, and so you could separate them by distillation. It's important to know what we've got. They, in medicine, could have very different effects on the human body. So it's really important to know where these things have attached onto our ring. And so there are some naming conventions. Now the IUPAC naming convention is to list them with the numbers, with 1 being at the very top and then clockwise around 2, 3, 4, 5, 6 as we go. But there are older names, because if you ultimately think about it, 2 and 6 are actually in the same position. It's just seen from the other side. I'll talk about that more in a second. But anyway, if you were immediately adjacent to the defining functional group, then you are in the ortho position. That's an old-fashioned word for positions 2 or 6. If you are in the 3 position or in the 5 position, so in the case of those deactivated aromatic compounds, in those positions, that's a meta position. But if you're opposite, and there's only one place where you can be opposite, and that is in position 4, it is in the para position. So sometimes you see ortho, meta, and para. Now, one of the things that we're going to have to take into the exam, having memorized, is whether or not a functional group is an activating functional group or a deactivating functional group. So if you think about the NH2, it had the effect of activating the group. It had lone pairs on that nitrogen that were not being used, and that enriched the electron density around that top carbon, meaning that subsequent substitutions would happen in the ortho positions adjacent to that carbon. There are other things that have similar setup, similar electron orbital structures that would activate rings. So the amine groups, which is the one we just talked about, the NH2, even secondary amines that have got NH, but then a long chain hydrocarbon, some sort of alkyl group attached where one of the hydrogens was, absolutely fine. That will still provide those lone pair electrons that will activate the group. Hydroxyl groups, OH, alkoxy groups, an oxygen connected to an alkyl group. And then alkyls themselves. So basically, if you stick a long chain alkane attached or something like that, fine. That will also have the effect of making that place activated. And of course, the halogens themselves have a slight effect of this activation. Now, alternatively, deactivating, those things that are going to naturally try to attach in positions 3 and 5, ketones will do this. Esters will do this, sulfonic acids, aldehydes, carboxylic acids, nitrile groups, nitro groups, and quaternary ammonium groups. These will all try and attach in those places. So why do we consider positions 2 and 6 both as ortho? Why do we see no significant difference between them? And it's actually because one is just the other one. They're actually the same. It's just seen from behind. Like if you looked at it like at face value and you put something in positions 2, if you walked around the back of it, well, that same thing would now be in position 6. They're equivalent. And so it's actually the same molecule. There's no difference in describing positions 2 to 6. You might say that yes, because of the functional group that's identified here, this NO2 group, that there's a double bond on one side and a single bond on the other, and therefore looking at it from behind is actually some kind of stereoisomer. It's like you've physically flipped it. It was left-handed before and is right-handed now. Not quite, because the single bond that connects the nitrogen to the carbon is of course rotatable, and so you flip it the other way and it will still look exactly the same. So what it means is, roughly speaking, is that 2 and 6 are equivalent positions. They're both called ortho, and there's an equal likelihood in an activating species that either of those positions could be filled. And then there is an equal likelihood to either of those positions filled as a para position filled in position 4. It means that whenever we generate something, whenever we do a substitution like this on an activated ring, we tend to get an equal amount of things in positions 2 and 6 and 4. But because positions 2 and 6 are the same, we tend to therefore get a ratio of products with an ortho isomer arrangement as being 66% or 66.6% and a 33.3% on the para isomer structure. So here's a real-world example of that. Phenylamine. What would happen is we would get 66% of the structural isomer, which would basically be 2-bromophenylamine, and we would get 33% of the structural isomer 4-bromophenylamine. So we'd get 33% of the paraphenylamine, bromophenylamine, and we would get 66% of the ortho-bromophenylamine. Chemical synthesis is about creating a new chemical, and what chemical we get quite often is determined by the sequence of chemical reactions we expose our ingredients to. Here we've got benzene, and we'd like to turn it into 1-chloro-4-nitrobenzene. So what should we do? Well, there are two groups attached to this benzene ring. There's the NO2 group and the Cl group. So what we need to think about, and this is the key thing, we need the first substitution to direct the second. So we want very specifically it to be a para molecule, with the Cl being opposite in the number 4 position to the NO2 group. So we've got to attach one of them before the other one, but which one could we do? So consider option 1, attaching the NO2. So in this case, we would heat with concentrated nitric acid and sulfuric acid. The sulfuric acid would help the nitronium ion form, which would be an electrophile, which would attach itself to the ring, as we've discussed before. But because of that positive nitrogen dipole that we see within the NO2, we would find that the electron density near the carbon it has joined has decreased. It would deactivate the ring, and it would push the Cl into the number 3 position, into the meta position. So that's not going to work. That's not where we want the Cl to be. So we're going to have to consider a different way around of doing it. What if we did the Cl first, the bromination, the very first electrophilic substitution reaction that we looked at in the presence of a catalyst? We would heat it up and we would attach the chlorine by direct electrophilic substitution. Now, chlorine will actually have a large electron density in the region. It's something that would activate the ring. Now, this would mean that it would create a situation where the subsequent addition of NO2 would either go into the 2 and 6 and 4 positions, which is the ortho and the para positions. In fact, it would do all of those. But because, of course, there are two possibilities for the 2 and 6, the ortho position, we're going to get that chemical produced at a ratio of 2 to 1 compared to the para, the number 4 position. So basically, we're going to get the desired chemical, but it's only going to be 1/3 of our yield. It's only because the other 2/3 of it is going to basically be the ortho version of this chemical, with the chlorine basically adjacent to the NO2 group. So how do we separate it? Well, we have got the chemical we desire to synthesize, but unfortunately it's now a mixture with other isomers of the same chemical. And so here we rely on the different boiling points of the different chemicals, and we would distill it. A fractional distillation or something similar to basically separate by boiling point the two chemicals, and then you would end up with your 1-chloro-4-nitrobenzene. What about synthesizing this trinitrotoluene, or TNT as it's otherwise known? Well, we're going to start with toluene, which is the old-fashioned name for methylbenzene. You can see that that is just a single alkyl group attached to the ring there. The very next step is we need to get the nitronium ion to form. So in sulfuric acid and nitric acid at about 50 degrees, we warm it up. What happens is the sulfuric acid helps create the nitronium ion. The nitronium ion is an electrophile and goes in there and adjoins. Now, it will generate a mixture of these three chemicals because of the very nature of it. The initial methyl group attached has activated the ring. And so therefore it's going to be in the ortho and para positions. In the 2, 4, and 6 positions, we will have an equal mixture of all three, which of course the 2 and the 6 positions are the same chemical. So we're going to have 2/3 of that arrangement and 1/3 of the other, as we've said before. But then we've got to consider what the next steps are. We've got one, all of our mixture just has one of these NO2 groups attached. So what's the next step? Well, we've either attached it opposite or we've attached it in the ortho position. The next step would be to add the next NO2 group, and if it's in the ortho, it will end up in the para position. If it's in the para position, the next one will end up in the ortho position. It all depends on which of the varieties of the single chloro-toluene that we've actually got. So what we find is the addition of the first one changes the properties of the ring ever so slightly. It has deactivated the ring slightly. It's slightly harder to attach the second one compared to the first. So we have to up the temperature that we're heating it to, but not by much. By just 20 or 30 degrees or so is enough to start having the second substitution occurring. Now, how do we get the third one on? The problem is now having 2 on has deactivated the ring really highly. Like, it is not attractive anymore to electrophiles. Getting the third one on requires to give them a huge amount of energy, and we would do this by basically making it very, very hot. A very high temperature, harsh conditions would basically give these chemicals enough energy to push together and the third substitution reaction occur. Now, since trinitrotoluene is a high explosive, excessive heating can lead to the explosions. It's actually very dangerous to create. It's dangerous indeed. Let's take a look at a historical example. During the First World War in London's Docklands, in the early evening, a factory making TNT exploded. And it was about 50 tons of trinitrotoluene exploded simply because it was overheated in that final stage. And the factory was almost completely staffed by women because the men were fighting at the front, and 73 of them died, injuring about 400 more. In fact, the explosion damage devastated about 70,000 homes in East London, and the explosion was heard for over 100 miles. Now, that sounds bad, but it wasn't the largest accidental explosion of an ammunition factory in the First World War, but it was probably the most devastating because it happened in densely packed suburbs. So we have to be very careful. If we misunderstand the chemistry and we get it wrong, then what could happen is, well, we could have a ginormous explosion.